this is the Switching Routing Wireless Essentials CCNA 2 version 7, module 14, routing concepts. Bob Sampson presenting. Okay, so we got a few slides here. There's about 50 of them, something like that. And a lot of it has to do with just what the title is, routing concepts. And we've talked about routers. We've had routers. We've seen routers in our configurations. But now we're actually going to get into doing the idea, kind of like we had the switching concepts back in module 1 of the semester 2. Now we're doing routing concepts. So the idea of a router, what's its purpose in life, is to do path determination. It's supposed to figure out how to direct traffic to destination IP addresses. Unlike a switch, which learns from uses both the source and destination MAC addresses, the switch processes those. A router doesn't care about source IP addresses. Routers look at destination IP addresses. They don't learn about where a network is located from a source address. Doesn't matter. Unlike a switch, remember that's how the switch does it. The router learns about other networks because it talks to other routers. They use routing protocols, which we'll get into later in this module. So the router can do that, but but it processes packets based upon destination IP addresses. Because the whole purpose here of the router is to determine where do I send this particular packet in order to reach its destination, the destination address, destination IP. And it also, one of the other functions is to maintain that, forward it, and up here somewhere, no, it doesn't have it on this one, but it's to maintain those paths. That's kind of the main things it's supposed to do. So there's a sample routing table. It's a little bit small here that has a couple of directly connected networks. It pertains to this network up here above. You can see router 1 and router 2. A little router 1 we're showing here that we're doing a show IP route. There are all these codes up here. They pertain to what's in the left-hand column of our routing table entries. You can see that there's 2 capital C's. Capital C up here tells us that those 2 entries that are in the routing table were directly connected networks. And there's a capital S, which happens to be the next one over here, which is that was a static address. And a static route gets placed in the routing table. Well, it doesn't get placed in the routing table. It gets placed into the configuration by a network administrator. Their static routes are manually configured routes that are configured in there by a sysadmin. That would be you folks, actually. And so in this example, router 1 only has direct knowledge about LAN 1 and LAN 2, 192.168.1, 192.168.2, the 2 directly connected networks on these 2 interfaces. We can see in the routing table that those first 2 are listed there. The entire network, remember back when we talked about IP addresses, we said that very, very first address, the network address, you can't assign to a workstation or to a router port or anything like that because it's used by routing protocols. Well, here's where it's used. The routing table consists of entries that can be interpreted as a range of addresses, but they're written in there as a starting address and a subnet mask, or in this case, a CIDR notation, and that's what it uses to calculate the scope of that network range. So in this example, this network begins at 192.168.1.0, and a /24 tells us that there's 256 total addresses. So it's basically anything that begins with 192.168.1. And from router 1's perspective, it knows to get there, it needs to go out fast Ethernet 00. Now it also says, hey, that's directly connected. So that is this network. From this routing table, where my arrow is pointing, we could actually add a label to this diagram and say, hey, that's fast Ethernet 00. Even though it's not on the diagram, we can tell that that's what it would be, that's where fast Ethernet 00 would be, because it's got it here in the routing table. We come down to the next one, and directly connected is 192.168.2.0. And which interface is that? Well, it's serial 000. It's directly connected. But this network over here, 3, Router 1 has no idea that exists. Network 3 over here is a unknown to Router 1. So we have to tell, Router 1 has to find out something about it, has to know where it is somehow. And so we've configured a static route in Router 1 to say, if you want to send traffic to 192.168.3.0, from Router 1's perspective, go via, meaning go across or through, this IP address, 192.168.2.2. Now that's something called a next hop IP. It is the address located on a next hop router. The concept of, and I'm saying that kind of emphasizing that, a next hop router is the next one in line, not my router. I'm not a hop away, I'm here. But imagine like a frog going across lily pads in a pond, going hop, hop, hop. So the next hop would be, where's the next router in line out a given path or a given interface. So in this example, router 2 would be the next hop router, and your static route says go to the next hop IP, meaning the IP address that's on the other end of the common link. Now, it can't be just any old address out on that next router. It's got to be a common link to our router. It's got to be across, in this case, the 192.168.2 network. So now Router 1 knows how to get to all the addresses, everything possible in this network. You would configure Router 2 in a similar way. It has direct knowledge of 2 of the 3 networks in this example, but it doesn't know about the 192.168.1 network. So you would have to do a static route in Router 2 so that its traffic could get redirected over to Router 1 to be delivered out to the left-hand LAN in this example. How do you make these things? We learn about them in about another 30 slides. So the routing table is going to be interpreted based upon the longest match, the best path. When they say the longest match, they mean any entry in the routing table that's going to start with the longest or the most or the highest number of ones in the subnet mask. It'll be the highest numeric value on a CIDR notation, which corresponds to the highest number of ones. It also refers to then the smallest subdivision that we've created, because the more network bits you've got, you're narrowing down and creating more and more networks, which means each one is smaller in size. And so the idea here is that you could possibly have a network or more than one that is a subnet, and that subnet is not located with all the rest of the networks, with all the rest of the IP addresses from its group. Let's just say, we'll keep it real easy, that it was 192.168.10.0. So there's a total of 256 addresses. And we made some divisions of it. Well, actually, we got some samples coming up, but the idea here is that you might have a summary address that says, hey, all of 192.168.10.0 is over this way, which would be a /24. But you've got one of those subnets is incorrectly been placed somewhere else, and it's a /28. Let's just say that we created several networks, several subnetworks, and one of them got assigned way over here where it doesn't belong. So inside of my routing table, I want to encounter that subnet first and properly direct traffic to it, even though it should be with the rest of the group, so that my router that is learning this information only should have one entry in it, not multiple entries, including this one that's way the heck over here where it doesn't belong. So what this is remember, the router ultimately is not trying to grade you on whether or not you've programmed your network correctly. The router is trying to deliver traffic to destinations. That's what it wants to do. And if you happen to have configured it a little wonky, it still can figure it out. And the way it's going to do it is going to say, all right, this particular subnet or subnets that have more ones in it, so that we know that that's a smaller piece of this larger classful, in this example, address. And so it will look to the longest match first and then work its way back to the largest in scope entry. We'll see it. Here comes a slide. I think it's right here. Yeah. The destination 172.16.0.10. 172.16.0.10. In binary, here's what it looks like. That's 172 here, 16 here, 0 here, and 10 here. And we have several entries in our routing table. This very first one in the routing table, notice they're all the same IP address. It's just how many bits are they checking. Whatever this entry goes to, wherever this one's said to go, is the one that it's going to use, because the first 26 bits, they're highlighted here in darker color. It's hard to see. But those first 26 bits match. They match here, but they match here. It's been told to look. This entry in my routing table said, find something with the first 26 bits that have these patterns. Well, this has those patterns all the way to right there. They match. So this, whatever route this said, whatever the destination for this was out over here, is where this particular router would send that. Now, maybe, there's another entry here that says, well, they're all this /18, a big block of addresses. This might say go out fast Ethernet 00. This one might say, oh, go across serial 00. There's somewhere else. Well, one got misplaced, and just because this big hunk of these is over here does not mean that I still would want to exclude routing to this one. So it's going to look to the longest match first, the longest number of subnet bits first, and then work its way back. All of these will match at some point. This one matches the longest, though. That would be the first. If this was 192 or 172.16.1.10, if this was a 1.10, then there would be a 1 right here, and this entry wouldn't match, but this one would, and this one would. So it's just a matter of, I guess the best way to, so this explains it, but just to understand the concept that it's going to look from the longest number of bits to the shortest number of bits required for a match. Most entries will only have one. You're not going to have multiple entries that would match. Properly, if your network's all proper, you shouldn't have that. Secondly, for IPv6 is the same thing. 64 would be a normal subnet. 48 would be a somewhere in between. We're getting into a this would be actually the global routing prefix, 48 bits. 40 over here is you're matching somewhere out on the internet. If you're only matching 40 bits in there, remember 48's the minimum you should have in your routing table. The minimum you should have is 48. It represents your global routing prefix. So I'm not sure how they snuck that one in there. That's an ISP's problem. So the routing table is going to be built by the router itself. It's not built by any particular routing protocol, but it is built by the router from information that it learns from all over the place, and then it makes a table of that information, and it picks from the table which routes, which networks, and which routes does it want to put into the routing table. Directly connected networks are going to be the first ones that it puts in the routing table. It's got the most confidence in those because it can reach out and touch them. They're on this network. So remote networks can be reached a couple of different ways. They can have a static route. We saw that already configured once where it says, hey, if you want to get to this network, go here. That would be one that was configured by a sysadmin. That's the next most desirable, and there's a way that it ranks these, and we'll have that coming up. It's called administrative distance. We actually saw administrative distance back in semester 1. I think it was in module 8 when we were talking about layer 3, the network layer. We mentioned administrative distance in there, that routers make their decisions based on that, and then we kind of forgot about it. But now that we're getting into the next couple of chapters, which specifically refer to routers and routing tables and path decisions, administrative distance will come into play when the decision's made as to what gets added into the routing table. Static routes are the next best thing to directly connected. For some warped reason, the router considers the fact that you programmed this or somebody programmed this, that's gospel, and it's gonna use that as the path. We'll talk much more about static routes. That's what the rest of this chapter and chapter 15 or module 15 are about. Not the rest of this chapter, but it comes up again. Dynamic routing protocols, OSPF, EIGRP, RIP, ISIS, IGRP, pick something, BGP. Those are dynamic routes, and they are learned and categorized by administrative distance as to how good they are, what they call the trustworthiness. Then there's a special kind of static route that's called out here on slide 8. It's called the default route. And a default route is a route. It's going to be in the routing table. It's not quite a default gateway. The default route is the path to follow if there's no match in the routing table. Kind of similar to a default gateway on a host that says, hey, if I've got a destination IP I'm trying to get to and it's not within my LAN, my subnet, I'm supposed to forward it to my default gateway, which is the router port. At this level, though, the router has a table that says, here's how you get to all the known universe, or at least in our case, what we know about in our LAN, in our local area network. And there could be 10 entries, there could be 2 entries, there could be 100 entries. What you don't have in that list is everything else. You don't have the internet in your list of routes, because ultimately, at some point, your LAN, your autonomous system, they call it, has to leave your little environment and go to an ISP. And at that point, in most cases, especially at this level, there's only one connection that goes out to your ISP. Imagine your home network. You only have one connection to Cox or Quest or whoever's supplying you your internet connection. So you don't exchange routes with Cox or with Quest and talk about routing updates and stuff. It doesn't matter. They give you one address, they track where it is, and you don't care. So the same thing happens if you go with something like the BA building, our building we used to be in before all this happened. We had routers in the BA building. We had networks in the BA building. And when we had a default route that said, if there's no match, in the routing table for the networks that exist in the BA building, then send it across the link to the IT department. We did not exchange routing updates with the IT department. Even though we're running a routing protocol and they're running a routing protocol, there was no need. There's only one path. There was only one wire, or actually it's fiber, that left the BA building. Out of all those networks and all those routers and all those switches and all that stuff that's in there, ultimately it left the building through one tiny little piece of fiber. Everything went across that piece of fiber. And it goes over to the IT department. So we didn't need to exchange routes with them because the answer would always be the same. If it's not an active LAN or an active IP subnet within our building, go to the IT department. That's the only answer. That's whether it's somewhere else on our campus, whether it's somewhere else in the district, or somewhere else in the world, go this way. And so that's what we did. It's called a default route. It will be the last route checked. It's going to check everything else in the routing table first before it gets to that. That's because the default route has a /0 as its prefix length. It is by definition, it has the shortest number of network bits. It'll check everything else first because remember, it starts with the highest number of network bits in an entry in the routing table and works its way back to the lowest. Well, a default route has no network bits. It matches everything. So you don't want it to be the very first thing checked. You want it to be the last thing checked, and it will then forward traffic based upon where you've told it to go with that default route. We'll see that a little later. It's just a type of routing entry. So we just jumped over this one and we went to this one. So here's kind of a broken down as to what, here's the destination address. It's going to go through the routing table. If there's absolutely no match, it's going to go to the trash can. Now that does not mean that there had to be an exact match. That just means that it had to hit maybe the default gateway. I'm sorry, I apologize, the default route. The default route, because the default route is going to be the last one at the bottom of the list. If it does find a match, if it's a directly connected network, it'll send out an ARP request, build up a frame, and send it to the host that's directly connected. If it's a distant network, it'll still build a frame, but it's going to deliver it to a next hop router. It's going to go through the routing lookup process. It's going to repeat this whole same thing again and go on to its next hop until this thing reaches its destination. So there's an awful lot going on as traffic passes through router to router to router, and you'd think it would take a lot of time to do that, and it does. I mean, it does occupy time, but the routers are really efficient. They know what they're doing, and they do it well. Jason, I see an unmute.
Yes. Are you the one who configures the default route, or is that done by the routing protocol?
Okay.
Or by the router?
Well, that's a really good question. And I will answer it, and we'll see it later on, but let me answer it. So typically, there will only be one router with a static route. It's just another form of a static route. It's a specialized form of a static route. The default route is still a static route, and a static route is configured by a network sysadmin. The only router that will have that configured manually, where you'll put it in as a static route, will almost always be the border router, the one that is on the way out, the edge of your network, where there's only one connection left that goes out to your ISP, or at least goes upstream heading towards your ISP, where you only have one possible path. That one router will have a statically configured default route. Then your dynamic routing protocol will take over, and it will propagate that route along with all the other routes for all those networks where it's going to dynamically learn them and pass that information around. It just becomes another network that's being sent out to all the other routers. So along with knowing how to get to 192.168.1 and 2 and 10 and 12, it also knows how to get to the default route and pick the best path, and it's dynamically maintained within your network, within your LAN or LANs, within your autonomous system. That connectivity or the path to follow will always be constantly being updated, so that if something goes down, it can adjust its path and still send packets to get out of the network. They all have to make it to the border router. So the border router has the manually configured route, and then the dynamic routing protocol will send that out to all the other routers in your system, so they all have that default route in their routing table, but the path that it's supposed to follow is no longer manually configured. The dynamic routing protocol calculated it. Did that answer your question?
It did. Thank you.
You're welcome. Thanks for asking it.
I've got a question as well.
Sure.
Building on that answer, at what point, since it sounds like there will always be a default route, when will there not be a default route and then sent to the trash can?
Really good question. Thank you, Hermes. Probably never. I mean, in a good network, in a properly configured network, there should always be a default route. Well, okay, let me rephrase that. If you don't have connectivity to the internet, there won't be a default route. There's no need for one, because you can contain all the updates within your network, and you don't need to have a way to get to those other 100 million addresses or whatever it is out there. Actually, it's more than that. So that would be the only time. But who has a network that doesn't go to the internet? So I guess the broader answer there would be your network will probably always have a default route. Make sense?
Okay. Yep. Thank you.
Okay. Yeah, good question. So we're going to break down a couple of these from that previous slide. A directly connected network is one that's configured on the router interface. So it treats them as a capital C in the routing table. It ends up as a capital C in the routing table. And it will have that entry, and it will say, it doesn't even have a via, it doesn't have to go across to anywhere. It is here. So it knows that, and it puts that in as a directly connected network. The difference there is that it would have to do an ARP and an encapsulation to get it out to the host on that network. I guess you could have a directly connected network. We saw it in the previous slide there, this previous diagram of that serial link. That lightning bolt's called a serial link, or a WAN connection between the two routers. And for that one, I just came up with, can everybody still hear? I show that I'm transmitting. Why did my audio conference come up? I'm just going to close it, I guess.
My window came up too, but we can still hear you. Right now.
Sure.
Oh, okay, so it wasn't just me. I still show the recording is working. I still show that I am speaking, and it sounds like you can all hear me, and I can hear you. So, hey, let's keep on going. So this forwarding a packet to a directly connected network, pretty straightforward. Fong, you're on mute. Did you have a? Oh, I guess not. Okay.
Oh, that was just a response to you, but thanks.
Oh, okay. You're welcome. Thank you. And a directly connected, it'll just encapsulate, do an ARP, get the host MAC address, and encapsulate. If we're going to a next hop router, it may still have to ask about or get a MAC address, because it's still got to make a frame to go across the link. I mean, you still have to have a data link frame to go between devices. And it's just in the case of a serial interface, it's not going to have MAC addresses, and there's all sorts of other, not other things, but it does have layer 2 addresses, but they're not MAC addresses in the case of a serial link. And we learn about that in the next semester in CCNA 3. So but we do have to still build a frame and deliver that. It's just that's not the ultimate destination. It's just a waypoint. And there's that other idea, drop the packet if there's no match in the routing table, but as we just discussed a few minutes ago, there probably will be a match somewhere, even if it's not for a specific network, but very likely for the default route. So what do? Primary responsibility is packet forwarding. We already talked about that. And to do it, it supports 3 different processes in here: process switching, fast switching, and then Cisco Express forwarding. So process switching, notice that every packet that comes through has to come up through an inbound interface. It comes in through this interface. It might have to pass through an access control list. We don't know about those yet. We learn about them in semester 3. But it might have to do that, which can add some latency. It would then go up here through the control plane, where it's going to make a path decision. It's going to look down that list and go, do you match? Do you match? Did I find a match? It's got to do a bit comparison at however many bits, 28, 26, whatever, and look to see if all 28 or 26 of those match an entry in that routing table. And it's got to go from one to another, to another, to another. And then when it finally finds a match, it goes, oh, this bit pattern matched. How do I get to where you're telling me to go? Oh, go out this interface or go to this next hop IP. Then it would go to that interface, and there might be an exit access control list also. So this adds latency. And this is going to happen this is an old process switching. Notice it says an older one, we don't do it. But for every single packet coming through. Adds a lot of latency, a lot of wasted time. If you consider that like a 1.5 megabyte file, 1.5 million bytes, which is like a small selfie picture, that's not that big a file anymore. And I'm sending that across my network. Well, remember that the session, or the, not the session layer, the transport layer is going to break down my data into pieces. And those pieces are going to be the size of what's called a maximum transmission unit. And that's typically 1,500 bytes. Well, 1.5 megabytes divided by 1,500 bytes per segment means we're going to make 1,000 segments out of that one little file. And each one of them is going, so that one little thing is going to have to do this 1,000 times, and that's just one little data stream. So it would be really nice if we could do something to speed that up. Well, let's move to the next slide, slide 16. Fast switching says, oh, wait a minute, another older packet forwarding mechanism? Oh, okay, well, let's at least see what it does. It says, you know what, you come in, and we're going to do the analysis, and we're going to go through that access list possibly, and we're going to go through our lookup table. This first time through, exit interface, exit access list. But in the meantime, when you stepped foot across here, did you see the security camera? It took a picture, not literally, of your frame of your layer 3 header. And the layer 3 header at source and destination MAC or source and destination IP addresses, and it's got, we learned all about this back in like I don't know, module 8 or something in CCNA 1, what's in that header. And so kind of like how a switch has the CAM, content addressable memory table, where it can do a very high speed lookup to match the 48 bits that make up a MAC address. This says let's extend that to layer 3, and let's say that we have this thing called fast forward cache or fast switching cache, and that's performing that same idea, except we're doing it on the layer 3 header instead of a layer 2 MAC address. And the reason why is in that last example I gave where I've got 1,000 of these packets coming through, the layer 3 header on that entire data stream, it's going from one point to another. The only difference in that in each of those packets, layer 3 headers, is going to be the sequence number. Well, that makes sense. That's how it keeps track of them. And the frame check sequence. Everything else is the same. So if it's already been through all the processes necessary, why do it all again when you can just say, hey, fast forward cache or fast switch cache, have you seen this layer 3 header before? Nope. Okay, go through the works. Next one comes in and says, hey, have you seen this? Yep, interface 12 or interface whatever. Just go straight through. So now you're making layer 3 forwarding decisions at the speed of layer 2 switching. It's called a fast switching cache. And it's older and we don't use it as much anymore. Really? What could be better than that? But wait, here it is. Cisco Express Forwarding in slide 17. Whoa, we don't even go up here and look this up. We don't go through that process. What happens is the router in the background creates this thing called a forwarding information base where it is creating or tracking outside of data communications. It's establishing the paths it needs to path to get to all possible destination networks in its in the network. So it's pre-creating. It's actually anticipating that at some point you may want to go to these. So let's set up a fast forwarding cache essentially that's called a forwarding information base. And let's keep that in here. And as long as the topology doesn't change, the answer is always going to be the same. So we can very quickly, we don't even have to go through the first time. I've already done that work, and I can just immediately apply this to the first packet as well as all subsequent packets. So it's very similar. Go back one slide. It's very similar to this, except this first packet going through this has already been taken into account and is just waiting until, if there's a change, a topology change, it's going to have to recalculate it, but otherwise, it's already got the information. There is even another one. Well, I shouldn't. Oh, what the heck, I let the cat out of the bag. They even apply Cisco Express Forwarding instead of having a single forwarding information and adjacency table. They make one for each interface. So it's not even a shared common thing. It's actually on an interface by interface basis, so it's even quicker. Okay, so we're going to do a basic router configuration review, and then I think we're not ready for a break quite yet. So the basic router configuration review, we're going to use this rather complex with these little tiny Bible-sized print parts, and we'll see some configurations for router 1 and router 2 in the next few slides. So slide 20 gives you one of the best and most comprehensive reviews of router configuration. Remember, over here on the left-hand side, all of this is the exact same stuff we do in a switch, except we would say VTY 015 instead of line VTY 04. In a switch, we go to 15. Other than that, all of these, substitute an S in here for the R, would be the commands we would put on a switch as well as a router. So that's a good review right there. Slide 20, really cool. Notice even the banner message of the day has multiple lines. They're separated by this pound sign and that pound sign, those things called delimiters. And there's multiple lines in the banner message of the day. So really cool stuff. Over here on the right-hand side, hey, they turned on IPv6 unicast routing because we're using a dual stack here. That's an often overlooked command. Then they actually put descriptions. Thank heaven somebody finally insisted on having descriptions on each of the interfaces. That's a person after my own heart. And then they put an IPv4 address in and an IPv6 address in and an IPv6 link local address. They defined that. They turned the interface on. Oh, this is beautiful. And then they did the same thing for the next interface and then the next interface. And then finally they got all done and they did a copy run start. So these are great examples, and you'll notice that the link local addresses are all the same on each one of these. That follows our oh, no, they're not. I just noticed. That's ::1:A, ::1:B, ::1:C. Oh, how did they sneak that in there? All right. Well, I was doing so well. Because very typically you will make the link local address you specifically use the same address on all interfaces. I guess this is close to the same. This router would be FE80::1, in this case ::A, B, or C. And another router might be FE80::2 or 3 or something like that on each interface. Also, keep in mind IPv6 addresses. Notice there's two of them here. One specifically a link local, but you could have multiple IPv6 addresses on a single interface. We can only have one IPv4 address, but you could have multiple IPv6 addresses. And you'll want to be careful that you don't do that accidentally, because unlike IPv4 that'll just overwrite one, IPv6 does not. Some show commands that are kind of handy. Some show commands with the pipe symbol, we've seen this before, that you might use to specify different levels of output or starting at certain places. Let's talk about the routing table and some of the processes we've already seen. So first of all, the routing table is built by the router, not by the routing protocol. It's built from a collection of information that it's gathered and keeps in a database of all the different routes, the different possible routes, and it could learn about them as directly connected or statically configured or different dynamic routing protocols. Actually, that's the three that it would find. They're outlined here: directly connected, static, or dynamic. But I could have multiple dynamic. I could have RIP and OSPF and DIGRP all running at the same time on the same router, and learning about the ways to get to different destination networks. Frankly, there would be very little cause for this, but you could do it. So those are all going to go into this big giant database that it's got, where it can sort them based on the administrative distance. It does a first sort based on the network address, then the administrative distance, and then the actual cost for each of those routes. And once it does that, it knows which ones to present to the routing table to be placed into the routing table. So there's the left-hand column in the routing table will identify whether it is a local address. This is not a link local address. We'll see this on a little bit later slide. Whether it was a directly connected network, whether it was a static network. This was an OSPF routing protocol. There's could be an I here, an R here for RIP. So there's different ways to identify how that network got brought into the router. If it's a static route or a default candidate route, candidate default route may not be a static route, but it'll have an asterisk next to it. because that's what it's trying to use as the default route. Principles about the routing table. Slide 25. Every router makes its path decision, its routing decision on its own based on the information in its routing table. So my routing table on my router could be totally different. Well, there's the next one. That my routing table could be totally different than your routing table, depending upon where we are in the network. I mean, you may have networks that are directly connected, and they're not directly connected to me. They could be part of a summary address. They could be, something else. So the routing tables may not be the same, but in a properly functioning network, every router will have a way to reach every other network address in there. Whether it's a summary address, whether it's a default route, whether it's a directly connected, every routing table in a properly operating configured, what they call a converged network, will have a route or routes to make it to a destination. The last one is that these are some of these axioms of routing. The last one here is that the router, just because you have an entry in your routing table that defines a path, does not mean there's a return path. And if there is a return path, it may not follow the same path you followed to get there. There's no little trail of breadcrumbs. There's no string that they pay out behind the packet to make sure it can follow it back. The routing, just because you have a path to get to some destination, does not mean that there is a way back. And when we get to troubleshooting routers and troubleshooting router installations, that becomes a key point, because you have a ping that doesn't go through, and then you finally do a trace route, and you go, well, wait a minute, it made it. The trace made it, but it didn't come back. The routing table entries are up on slide 26. Here's an OSPF. You can see an O here. That's the route source. Here's the network that is referred to here that it learned about. It learned about the 10.04.0 network. /24 tells us that the first 3 octets make up the network address. The last octet would be used for hosts. This 110, this number 3, is the administrative distance, the AD. We will see that coming up in a subsequent slide. But OSPF has a 110 AD. Remember I said this will all get dumped into like a giant spreadsheet where we'd have the address and its subnet mask. Then the next column would be this, and then the metric or the cost would be this one. And then it's going to sort them so that it would sort based upon, it's going to first of all group them by destination networks. Then it's going to look to see what the administrative distances are. The lower the better. So if it was just doing a numeric value sort, that would come up. Then if there was more than one learned route through OSPF, so this would be the same and this would be the same, then it gets down to the cost, because there could be 2 different paths potentially to get to that destination network that OSPF found. Which one's the best? This reminds me again, go back to Spanning Tree, where Spanning Tree picked the best path through the layer 2 network by assigning a relative cost to each of the links between the switches. That cost came off of a table, and the faster the link, the lower the number. So that when it added up all the different links it had to go through, the lowest cost was the path it took. Well, that's exactly what OSPF does at layer 3. I mean, basically, that's the same process. OSPF is going to assign relative values to each link, and it's going to add them up, and that's what's going to be this metric, is going to be the combined cost depending upon which path you take. The next one is the via, meaning how do I get there? That's the next top IP address. Then timer, how long has it been in the table? And then the exit interface. This IP address, via, is on the next router in line. This is my interface. So what I can deduce from this is that my serial 011 interface on this particular router that has this in the routing table, that the serial 011 network has this as a potential IP address. Not a potential, it is an IP address on the range of that network. I don't know what the subnet mask is. I can't apply this one. This is telling me the size of this destination network. It has nothing to do with my router. But this one, I know this IP address is going to be part of the network that is on serial 011, on my serial 011. Well, how far away is this? How many routers do I have to go through to get there? How long is it going to take? We don't know that. All we know is that the routing process has said, for your best shot, take this path, go this way. And that's all the further scope that we've got. IPv6, very similar, just a much bigger address here. Notice it used the next hop IP for the via address. It used a next hop. It used the link local as the next hop IP, not the full IPv6 style address. It used a link local, much shorter, much easier to use, and I think it actually processes it faster somewhere. I read that, but it's still out serial 011. So if we referred back about 8 slides to the topology for this, we could probably identify which router this was in by telling that it's got to go from, well, let's do it. To get to 10.04.0, it's going to go to 10.03.2. So for a router to get to 10.04.0, that the router that's got that in its table has to go to 10.03.2, right here. So that's this router out serial 011, next hop IP 10.03.2 to get to this network. That's what's in router 1's routing table. So that sample came from the router 1 routing table. Let's move forward. Probably this one did too. The directly connecteds will have a C next to them. We've already seen it. What we have not seen is a capital L. This is added by iOS 15. The version iOS 15 added in a local address, not a link local address. The local address is the actual fully configured IP address on the interface. So whatever it is. And it will have a /32 in the case of an IPv4 address. It will have a /128 in the case of an IPv6 address. It is looking for an exact match. Unlike the network, the C or the O or the whatever, the network interface, the network address is going to have the network address followed by a subnet mask that would tell it, or a CIDR notation that would tell you the scope or the range of addresses. This is only one address, and it's going to be indicated by an L in the routing table, not a link local address, just a local address. The link local is not in the routing table. You will not see it as a destination network. You may see it as a via. The link local may be shown as a via. We saw that in the last slide, but not as a destination network. Link local addresses are not routable. But a local address is used as part of a higher speed route lookup. That's all I could find for why it's important and why it's there. So I believe, that's what it meant, and it's just part of a higher speed lookup process by using a local IP that is the actual interface's IP address. We'll see it in the routing table coming up. The static routes, after the directly connected interfaces are there and added to the routing table, the static routes, because they have the administrative distance of 1, they're considered the next best thing. It will put them into the routing table. Now, we're introducing a concept here on slide 28 of the 3 primary places we will use static routes. The first bullet point on slide 28, these are going to be some important ones, and then we'll hit a break here. We're hitting about the 50-minute mark on this lecture, so I understand we'll take a break here. But I want to finish this part on static routes. That it provides ease of routing table maintenance in smaller networks that are not expected to grow significantly. Let me give you a clue. If your network has more than 2 routers in it, it's too big already to use static routes. I had to put static routes in the case study because we haven't learned about dynamic routing protocols yet. But if you've been looking at the case study and you've seen the section on static routes, just 3 routers with actually addresses that summarize to a certain extent. We don't even have to have each separate network. There's like 18 static routes in that stupid thing. I didn't mean to call my work stupid, but unnecessary. A routing protocol would maintain that in an instant and incredibly scalable. And it would adapt to changes in the network environment. Static routes don't. The only thing a static route knows is the exit interface or the next hop IP for my router. It can't see any further than that. This is why for like the default route, we don't configure a manually configured static route in every router in our network, because all it would take is a failure. Let's just say we're about 3 routers away from the border router, and you've got statically configured routes that have that default route. That's all well and good until a link fails that's not part of the 4th router back. Its link to router 3 in line works fine, but the link from router 3 to router 2 went down. Router 4 has no idea that happened, and it's going to still pump data up to router 3, and that's not good. So you'd want that to be a dynamically learned route. You would not want your internal networks to have static routes, unless, of course, you've got a very small network like 2 routers, where, like in our sample we saw, there's only 2, and then you could configure static routes. Much more than that, it gets way too complicated. So bullet point number 1, we're probably not going to do that. Bullet point number 2 is what we've already talked about. That default route is a specialized static route. It's going to be on your border router. The default route is going to be to get to your ISP, to get out to the internet, to get to just a larger portion of your internal network. Like I say, we had one in the BA building where we had a default route that went to our IT department. Now, they're not the ISP, they're not Cox Communications, but they're the next step we have to go to get there. So that's the default route. The last concept is called a stub network, S-T-U-B, like stubbing your toe. Actually, it's more like, if you're familiar with a plumbing term where you stub out the plumbing, it's like a dead end. You may have a pipe that leads over and goes up to a vent pipe and it stops. That's a stub. It's stubbed out. The idea here is that we have only one link to get to our network. Well, we've already talked about that. That goes out to our ISP. Your home network connects to your Cox or your CenturyLink or whoever's out there. You've got only one path in and out would make it a stub network. Now, behind that, behind your border router, I could have 30 routers. They're all talking to each other, and they're meshed together, and they're doing their thing. Great, that's fine. But ultimately, if you want to leave, there's only one path. So we've already said on that end, we're going to have a default route. That's going to be the path from the stub network's perspective. It's going to have a single static route that says, hey, the default route, go out this interface, it'll get you to the rest of the world. By the way, we're going to use OSPF to tell all the rest of our routers about how to get there, to come to me, but ultimately I'm going to have the manually configured route that says go out here. Well, there's a problem with that, because that link that goes to the ISP or wherever it's going, you're not exchanging routing updates across that link. OSPF's running down in my network, but I'm not sending OSPF updates to my ISP. It would just annoy them. And so at the ISP end of a stub link, they also have a static route. It's sometimes called a static summary route or a summary static route. Depends on which way you look at it. And so from the ISP's perspective, it has to have a way of knowing what addresses you've got hiding behind your border router, because it needs to know that information and know to forward destination packets that have that destination IP address. It's not going to learn them from a dynamic routing protocol, so it needs to have a manually configured address, not a default route. It's going to be what's called a summary route and say, hey, This whole block of IPs is that way. In the case of the BA building in the IT department, the BA building had a quad 0. Oh, I said the words. It comes up on the next slide, I think. That's how you define a static route. It's called a quad 0 route. That's how you define a default route. It's called a quad 0 route. But let's just say we got a default route. We're going to call it a default route. That's what we know so far. The BA building had a default route that said, hey, if it's not in our network over here, go that way. The IT department has a mirroring or a relational route. Remember, no routing updates going across the link that says, if I want to get to this particular block of IP addresses, I have to go down this line because that's where they're located. And those are both manually configured at each end of a stub network. Even your ISP, if you're your home network, they have to track what IP address they've given you, and internally they have to track how to get to it. You are a stub network to your ISP, to Cox or to Quest or whoever it is, that CenturyLink and whatever name they're using this week. I go back to when I think when I first got here, they were called Mountain Bell, which was 55 years ago, so it's been a while. So here's an example of static routes on slide 29, and we get to the configuration, the syntax for how to configure a static route. So on slide 29, we've got two different static routes, one for IPv4, one for IPv6. The syntax is global. We're in global configuration. You do not configure a static route as part of an individual routing protocol. You do not configure it as part of an individual interface. It is configured globally. And the syntax is global config IP space route or IPv6 route. Well, you know, it's basically the same idea. You just plug it in different numbers. IP route, and the next thing that you're going to put in is the destination. Network and scope subnet mask. That's this first bracket, curly Q bracket here. IP route, this destination network, which in this diagram is over here on the right-hand side. So from router 1's perspective, to get to the 10.04.0 network /24, 10.04.0 network /24, to get there from router 1's perspective, go to 10.03.2. Router 1's perspective, to get to this network, go to this interface, 10.03.2. Same for the IPv6, except substitute in different numbers. To get to this big address here, go to this next hop IP address. That's what all this is. There's that 3:::2. Here's the 3 network: :::2. So that's these two static routes are both going to the same destination, ultimately to the network that's over here, to get to this network, not to this individual IP, not to this IP, not to that IP. To get to the network, go to this next hop IP. That's one form of the command. You could also say, there's another one you could do that says IP route. By the way, if you're doing the case study, these are the commands you need. Did I mention that if you're doing the case study, these might be the commands you need? IP route, the destination network, and its subnet mask. You can get them right off a chart. You can put in the exit interface here. Instead of next hop IP, from my router's perspective to get there, I go out serial 011. So I could do it with the next hop IP. I could do it with the serial 011. Or if I wanted to make it something called a fully specified, I would put both. Fully specified would still be IP route. They're all going to begin the same. Up till here, they're the same. It's IP route followed by the destination network and its subnet mask. It's just what happens after that. Next hop IP, exit interface, or both. And they'll be spelled out that way in the instructions. Either go to the next hop IP, go to the exit interface, or do a fully specified, which means use both. That information should allow you to do all the case study configurations, because that's kind of how they're spelled out in the instructions. They tell you which network to go to, which router to program it in, what's the destination network and subnet mask, and whether it's an exit interface, a next hop IP, or fully specified. So it's just kind of a fill in the blanks to create the static route statements. If you make a mistake, be sure to remove the static routes. There can be more than one, which would mean that even your mistakes live on. And they're still there and they're still active, and they could be throwing off your routing because you might have said, hey, to get to this network, blah, 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 go out gig 000. That command is still in there. You fixed it, you put in another one and went, oh, that was a mistake. No, to get to this network, go out serial 001 or 010. Yeah, do that instead. That first IP route statement you put in is still there. So don't make that mistake. Do them. If you do put one in by error, remove it so that it's no longer in the table. Defining static route. That's the syntax of a static route. Slide 29.
So question for that?
Okay, let me go back.
To remove the static routes, you just add the no to the beginning?
Put the no right after that config. Just say no space and then IP route, blah, 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 blah.
Gotcha.
Perfect, thanks. Let's see, dynamic routing protocols, Let's stop right there. We're going to take a break. I'm going to pause the recording. Okay, so we've got dynamic routing protocols in here. We've learned about static routes, and we've learned about directly connected routes. Then there's the dynamic routing protocols. So now, for our same diagram that we've had before, you've got the two routes that we've been talking about, or the two routers we've been talking about. But now if we add in a dynamic routing protocol, and by the way, recall that if we were doing static routes just a second ago here, like this router would have had to have an entry for that route and an entry for this network. You know, we'd have to have two different static routes, plus a quad, or I said it again, plus a default route telling it how to get to the internet would have had to be configured here. Router 2 would have had to have these two networks plus a default route for it to get to the internet. Now this one's default route would point to this one's default route would point to that one. And then we'd have to have three static routes in each one of these. And if we added any more networks, we'd have to add more static routes. And if we added another router up here and we had a triangle, well, then we got multiple paths. Static routes do not hold up well. Dynamic routing protocol, we just tell router 1, hey, you know about your three directly connected networks. But if you wanted to have any others, we'll have router 2 tell you about them in this example. Through OSPF is the routing protocol of choice. So router 2 is going to tell router 1 about these two networks, and router 2 has a static route. Remember, that's one of the good uses of a static route is on our border router, the one that goes out to the ISP. So we would have a manually configured default route on router 2. And as part of OSPF, it would tell router 1 about that default route. It would also tell router 1 about these two networks. Router 1 would tell router 2 about these two networks and any others. If we added another network over here and added another interface or router on a stick, whatever it is, OSPF automatically is going to include that. And then everybody, and you could have 20 routers out here and they will all be updated. And by the way, OSPF will do that in milliseconds. I mean, it just almost instantly updates. And so very, very fast, dynamic, adapts to changes. So really, really cool stuff. That's a dynamic routing protocol. Here's what it'll look like in the routing table. Here's these O's on show IPv6 route. Here's the O for OSPF on the IPv4 routes, and you'll notice those capital O's, which was up here as an OSPF route. We had that directly connected in a local. Here's an O for OSPF, and there's even a bunch more, but the output was omitted for brevity. And then in the case of router 1, the answer is the same for both of those networks to get to the 10.4 or 10.05 network. You go to this next hop IP, out your serial interface. That's fine. I mean, you can have multiple entries going the same path, but that's what this is talking about. Via is the across or through to the next hop IP. This is the exit interface from our perspective. Also, there's that default route. So they spelled it out here that router 2 would have a statically configured default route, and we finally get to call it what it is, a quad 0 route. So it is a specialized form or a specific form of a static route. In this particular case, that default route would be an IP route statement followed by 4 zeros as the network address, 0.0.0.0. Put a couple of spaces in just so you can keep it separate. It'll take them out when it processes the command, but you can have multiple spaces, and it just makes it easier to make sure you didn't just keep going 0.0.0.0.0.0. You know, that's not going to work. So put in 4 zeros with 3 periods between them, put about 3 spaces, put in another 4 zeros with periods between them to represent the subnet mask. So it's a total of 8 zeros, or 2 quad being 4, 2 quad 0 entries for the destination route. That is the default route configuration. In an IPv6 router, it's : /0. It's much shorter. So IPv4 is quad 0, shortened down to you just call it a quad 0 route. That's mostly, I mean, you'll see it referred to as a default route or as a quad 0 route. That's what it's called. And so to configure it, it's the IP route command, globally configured IP space route, 4 zeros with 3 periods, a couple of spaces, 4 zeros with 3 spaces, and then from router 2's perspective, it either has a next hop IP, an exit interface, or both if it's fully specified. And then you'd run a dynamic routing protocol in R2 and R1, and that route would be exchanged or propagated to R1. In this case, there's only one path, but if there was multiple paths, it would pick and maintain the best path for traffic to make it to R2 to get to that quad 0 route. So again, the default route, and it's called a default route. It's got special properties. It's treated differently. We learn about that in semester 3. Right now, let's just learn about how you configure it and where we would use it. Why it gets treated differently is a process for semester 3 when we study OSPF. It was created using standardized but now obsolete classful addressing. Long ago and far away, we didn't have subnetting. The way you would tell what the network address was, and this is still how the internet works, by the way, is that you would just look at the value of the first octet, you would calculate what's the class full address, you would apply the class full subnet mask. That's why we learned all that stuff. And once you did that, you would know the network address you're dealing with. Well, then we got all confused and said that's very wasteful, and we need to do subnetting, and we have to do in between the classes. We have to be able to break it down, and we did classless subnetting, and the rest is history, as they say. But the IPv4 routing table is still based on class full. So when it creates a routing table, we're up on slide 34, you will notice that in the routing table, there is this entry. This entry does not contain an exit interface. If we expanded it out here, over here, it would not have, it's just going to say it's variably subnetted. It would not have an exit interface or a next hop IP. This is not a route. This is used as an indexing tab for the lookup process in the routing table. It's created by the routing table, not by OSPF, not by you, not by static routes. This is created by the router to put a tab in. As an example, on your cell phone, if I said call Bob Sampson, you are not going to start at the A's and look at all your A's and then look at all your B's and all your C's till you get to the S's. There's a little index tab down the side. You can jump right to the S's. Well, in this case, this is going to say, I'm going to look at my destination IP address that I'm trying to find an entry for. I'm going to compare it to the one that I'm pointing at up here. Let's just use an example of, I'm trying to get to 192.168.23.2. I'm trying to get to 192.168.23.2. Well, is 192.168.23? Nope, it's not going to be here. Well, by the way this is arranged, that means I don't have to look at all these. I can go to the next major entry, the next index tab. Is 192.168.23 in here? No, this is 12.0 through 12.255. It isn't here. I can skip these. And some of these might have 20 or 30 entries in them, you know, so I can skip to the next one. How about this one, 13.0? Nope, it's not here. What about 192.168.23.0? Yes, it should be here, but this is not an entry. This has no way out. I have to then say, okay, now that I found this entry, that tells me that I should look underneath this one. I shouldn't skip anymore. Oh, 23.2 would match this. This is 23.0 through 23.3. I would follow this path, whatever it is, because that's my match. But it uses these entries that are here as summary values, class full entries, to allow us to index or speed up the search process so we don't have to go through every single entry in the routing table. These are called parent routes. The parent route is created when we have subnetworks called child routes. The child routes are always the indented ones. The parent route is the outer dented one, or the only a single tab in, a double tab in, however you want to think about it. The parent route will not be there if there are not child routes. There can be routes that exist out at this level that are not parent routes. I might just have a single class full entry that was learned through a dynamic routing protocol, and that has no children under it, but it's still out here to the outside. So not every entry that has a single tab on it is going to be a parent route, but any entry that has subnetworks under it, under the class full, will be a parent route, and these will be called child routes. Child routes will always have an exit interface. They always have a way out. This was a directly connected child route. These two were learned via OSPF. See the O over here. There's an example of a local address and a directly connected. They're paired together. So this is an iOS 15 output. Here's the network address, and this is part of it. This IP address is included in this network address. However, this is a /32. It's the full local IP address. All 32 bits are being compared. Again, why does it do that? Because it can. So that I told you there'd be an example coming up that had a local address, and each of these directly connected has a local address also. That's the actual address on the interface. And then this is the network that has a scope or a range that goes with it. Some of these are /30s, some are /24s. As a side note, it's not in this curriculum. This is called a level 1 route. That's called a level 2 route. Level 1, you know, 1 tab in. Level 2, 2 tabs in if you're doing tabbing. And so that's another way to refer to these. Level 1 routes are not always parent routes. You know, a parent route is always a level 1 route, but not all level 1 routes are parent routes. There could be others. Child routes are always level 2 routes. That's the only choice they've got. So that's some terms you'll hear about the routing table. The only two they bring up in the curriculum, though, are the parent route, child route. So hopefully that's all you'll ever see or get tested on. But if you see something that refers to a level 1 route, imagine what the routing table looks like. That's going to be a 1 tab in, and a level 2 route would be a 2 tab in, which would mean it's a child route. The only level 2 routes you will ever find are here, and they're child routes. IPv6 does not understand class full. I mean, everything is basically just a route. There's no classes of addresses, and so they just have them in their routing table. It's just there's no indents, there's no parents or child or level 1, level 2, or default subnet mask. There's none of that. It's just a routing table. So here's this idea of an administrative distance, a capital AD for administrative distance. They say you'll see this term trustworthiness of the route. The lower the administrative distance, the more trustworthy it is. Well, you know, what is it, sneaky, or you loaned it money once and it never paid it back? How trustworthy is it? It's more, I think a better term would be the desirability of the route, because for instance, if I've got two destinations in my database, two routes that are the same route, I mean the same network, I've got ways to get to the same network, I would want to use the route that was created or given to me, presented to the database by the best routing protocol out there. And so they rank the routing protocols by different administrative distances, so that when you look at a whole bunch of them and it sorts them by the administrative distance, the lower the administrative distance, the more trustworthy or the better decision process, and then hopefully that's the one that will get placed into the routing table. So as an example, we'll see it on the next question or the next slide here. Here's the administrative distances for some of the things. There's more than this, but we already saw that directly connecteds are the most desirable. They have an administrative distance of 0. Nothing's better than them. Static routes, remember I said they're the next most, they're just right up there with directly connecteds, and the router maybe naively believes we knew what we were doing when we configured this static route, so it'll put that one in the routing table next. By the way, this is providing that the interface is up. You won't have an entry in the routing table if you can't reach that destination network. So like a directly connected interface that's down, either administratively down or down, whatever it is, if it's down, it won't be in the routing table. It'll show up in a show IP interface brief because it's configured, but it won't show up in the routing table unless it's a valid interface. So directly connected static route. Then here's this EIGRP. That's one of those routing protocols we've talked about. And there's a summary route in EIGRP, and then though the main EIGRP updates will come through as 90s. BGP that's what runs the internet. External BGP runs the internet. EIGRP, a 90, we'll see those. OSPF, if we were running OSPF, if we were running RIP. So basically, if we had destinations, if we were running all three routing processes on our router, so we had EIGRP, OSPF, and RIP, and they all learned ways to get to a specific destination network, there would be 3 separate entries in our routing database for each of these entries, but the one that it's going to choose, the entry it would choose to put into the routing table, is the one that was processed or learned by EIGRP, because it's got the best administrative distance. Well, what makes it so special? Well, first of all, Cisco wrote it. It's Cisco proprietary, so they're rather proud of it. Also, it uses 2 or more, but by default 2, different forms of decision-making for each route that it puts into the routing table. OSPF only uses 1. Now, it's a big one. It's called bandwidth. They use the speed of the links. We saw that already in OSPF, that it adds up the cumulative speed of the links. But an EIGRP does that too, but EIGRP adds in a second value. So it's considered slightly better. It makes slightly better decisions. You know, it's your 20-year-old child instead of your 18-year-old. They're a little more mature. They make better decisions. And so, but what if I'm only running OSPF? Well, then we don't got to worry about anything else. That's the route that's going to get presented. And so most of the time, that's what you're going to be running. You'll have directly connected statics, and because it's the only protocol we use, OSPF will be the other value you'll have. So we already talked about where we would use static routes. We've already got those right up here, you know, routing between stub networks. So for routes outside the routing domain not learned by the dynamic, that's called the default route, basically, those. No, that would be for getting to a specific route outside of your network. Well, the quad 0 or the default route will get it there anyway. So who cares? You know, that's an overlapping one. And when we want to define a specific path, maybe for security purposes, you might want to do that and say, I'm just going to make this the path you get to go through the network. We're not going to include it in dynamic. But that's what static routes. What do we use them for? A default route out from our network to from a stub network, because ultimately we're all stub networks. So you use a default route. That's one use. The other use that we know of that we're going to use them for is the other end of that stub network, wherever that is, to summarize addresses that need to come back, because there's no routing protocol running across a stub network. So what about dynamic routing protocols? When will we use them? In networks consisting of more than just a few routers, like more than 2. When a change in the network topology requires the network to automatically determine another path, like everybody should. And then for scalability, as the network grows, the dynamic routing protocol adapts very nicely. And that's why we should always use dynamic routing protocols, except for default route out of a stub and the summary route coming back. This just kind of compares those all over here. And by the way, if you see a question that says, which should you use for security, static routing is considered more secure than dynamic routing, because the dynamic routing protocol is advertising the routes back and forth and susceptible to a change or a bogus routing update. So, routing protocol been around for a while. Exterior Gateway Protocol back in 1982, and then RIP, the first well, IGRP was a Cisco proprietary. That came 3 years before RIP. So Cisco was really up here doing the first routing processes. EGP was a predecessor to BGP on the internet. Then RIP came along. Then IS to IS back in 1990, so that's 30 years ago. The OSPF that we use, called OSPF version 2, was 1991, 29 years ago, that routing protocol, followed very shortly by EIGRP, a new version of RIP, BGP to run the internet better, RIP for IPv6, BGP multi-protocol, I think that one's called, OSPF version 3, the latest version of OSPF for IPv6. They added that in 1999. And then way up here to IS for IPv6 in 2008. There's not very many modern routing protocols in here. I mean, the one we're using, OSPF version 2, is 29 years old. But it still runs and it still works, and routers that are 29 years old still exist out there. So you need to be able to go back to that backwards compatibility. So here's a way of breaking down and classifying routing processes or routing protocols. And the first major distinction is up here in the blue, whether it's an interior or an exterior. Well, let's start with the exterior and get it off the chart here. Exterior gateway protocols, it means the internet. Exterior, it's outside your network. They use BGP and BGP multiprocess or multi-protocol for IPv4 and IPv6. That's what runs the internet. You don't need to worry about that until you get up to CCNP. Then you learn about that. So these are off the table as far as we're concerned. So then we get down to interior gateway protocols, and you can see several of the ones we've been talking about in both the IPv4 and the IPv6 flavors. And there's a distinction here between distance vector and link state. So within the interior gateway protocols, there's two subdivisions, one for distance vector and one for link state. The primary distinction between distance vector and link state is how our routing updates routing information propagated between the routers. That's the main distinction between these two. There's a lot of other ones, but that's the primary one, is how are routing updates sent back and forth between the routers. Distance vector, which is RIP and EIGRP, and their IPv6 counterparts, they exchange their routing table with their neighbors. And the neighbor exchanges theirs back. There's no social distancing here. We're getting up close and personal. So they're sending their routing tables back and forth. Now, my routing table is based on directly connected static routes that were configured on my device and ones that I learned about from other routers. So then I'm propagating that information. I've got some direct knowledge of ones I know are right, but I may have learned from router 6 over there about some network they've got. I added that into my router table, and now I'm passing it on to you, your router 3. But what you're relying on is that I properly interpret it and have the best path to get to router 6. You're reliant upon that information being accurate because you're taking it from my routing table. You have no idea how I got it from router 6 or if it's even right. It's kind of dubbed routing by rumor. So I heard about this. One day in a bar, I overheard from somebody's sister. Well, the idea of telephone too, where you have a room full of people and you whisper a message in one person's ear and you go, meet me at the stadium at 9 o'clock in a pink shirt. And by the time it gets over to the other end, you're partying at a bar in a muumuu, or something. It's like the message just gets garbled, just going from person to person to person. In theory, the router shouldn't mess it up, and it shouldn't get garbled, and it most of the time doesn't. But that's how distance vector transfers information between the routers. Well, then what's link state do? What's the difference there? Link state, every router sends out an update about its networks, nobody else's. The link state router running OSPF sends out updates that say, I know about these directly connected networks, first-hand knowledge. And that is passed on to router to router to router to router. Well, that's just what the other ones are doing. No, the other ones are interpreting it, building their own routing table, and then passing it on. This one says, here's this one little link state update. It's just a little piece of paper, a Post-it note that says, hey, router 3 has this network on it with this subnet mask. Read it, add it into your database, and then pass it on. Don't modify it. After a short period of time, every router in the OSPF area will have a collection of little Post-it notes or the information from them that relates to every single network out there. Well, what can we do with that? We'll take them in your little 3x5 card file you've been keeping them in, dump them out on the table, and you can, the leg bone's connected to the shin bone, you can match them up and go, oh, this router's got this network. This router over here's got on the same network. I can draw a line between them. I can make a link between those two. And now I've got this one over here and this one over here and this one over here. And in a very short period of time, you could actually recreate the entire network from something called the link state database. And every router does that internally based on first-hand knowledge from all the routers in the network. It's not routing by rumor. And then from that digital map, it doesn't actually pour them all out on a table and draw chalk lines between them. It does it electronically. It builds a hierarchical structure, and then it can create the best path from that information. So that's the difference between link state and distance vector. And we've gotten to where this is the only one we teach, OSPF for IPv4. We don't even do IPv6 because basically the process is the same in IPv6. It's just bigger numbers in the routing tables. But it's the same algorithm running the same process. So what's it used for? What are dynamic routing processes used for? Discovery of remote networks, maintain routing information, choose the best path, and adapt if it fails. There's those data structures we talked about, that database where it's keeping those routing, the routes themselves. The messages going back and forth are typically proprietary to the routing protocol. Now, the routing processes don't carry user data. We have TCP and IP for that. We don't carry user data for this. They're their own little packets and their packet structure, and they communicate with the routers themselves. That's what they're talking behind your back. And they're not the only one. There's a lot of stuff going on in there. Once it gets to the router, an algorithm, which is the routing process, the OSPF process, builds the routing table and makes the database, the routing database, and then builds the routing table. Note down here at the bottom is that The routing protocols determine the best path or route to each network. It's offered to the routing table. The route will be installed if there's not another routing source with a lower administrative distance. I think I actually put that in there. Best path, we've already talked about what's the best path. Well, we're only going to use OSPF, so that's by definition going to be the one we're going to use. And with an OSPF, it's got this metric or cost, which is based on the cumulative bandwidth from source to destination. The faster links are assigned lower cost. Gosh, this looks more and more like spanning tree all the time. Remember we had that table that said a fast Ethernet port was a lower number than a 10 megabit port. The fast Ethernet was a 19, the 10 megabit was a 100, I think. And so you want to end up with the lowest cumulative cost. Well, that's how OSPF works. They have the same idea of assigning lower values to higher speed links, and then they add up the values. If I go this direction, what's it going to cost me to get to that destination network? Hey, I've got another path over here. If I go that way, what's it going to cost me? Oh, that's a lower number. This is the path I'm going to choose because it's less costly for me. It's a faster route. So that's what OSPF is doing, and we will study that in modules 1 and 2 of semester 3. So right now we're just introducing the concepts. RIP uses hop count. It doesn't care about the speed of the links. Now that's a really lousy routing protocol. I could have a gigabit link and a 128K serial link, and RIP thinks they're the same speed, and it will treat them accordingly. And so RIP is not used much at all. We used to use it as a teaching concept because it's really easy to read a routing table that says, hey, if I go this path, it's 3 hops. If I go that way, it's 2 hops. You can see it right on the diagram. OSPF and EIGRP have some pretty sophisticated algorithms that they're doing some pretty funky math. And you can do it. You can recreate it and see what it's doing. I mean, they're published algorithms, but it's not nearly as easy as looking and saying 1 hop, 2 hop, 3 hops. So we used to teach RIP only because it was easier to interpret a routing table, but that's not a good reason to try and propagate a really lousy routing protocol. Let's just teach OSPF and teach you how to read the routing table for OSPF. So load balancing, if I have equal costs to reach the same destination and they are the same cost, well then why not share the load? Hey, I'll send one packet this way, the next packet that way, this one, that one, this one, that one. And so I can balance the load to get to that destination. If they are unequal cost, the only routing protocol that supports that is EIGRP, and we don't learn about EIGRP. So for OSPF, they would have to be equal in cost before it would put both entries in the routing table. Hey, I like this slide. You probably like this slide too, because this slide means that we're done with Module 14. So, questions? Are we all still awake out there? I see an X. I see this. I've got a hand. Several people. All right. Okay. Any questions that this brought up? We will learn much more about static routes in Module 15. Not much more. We already know pretty much. 15's not the, we'll introduce a few, but that's, we will learn a little bit more about programming them and fully specified and, how do they fit in the routing table, but that's Module 15. But you know enough now from that one programming slide and the iOS command summary that you should be able to do these. Anybody questions? Nothing in the chat. I don't see anybody unmuting. So I am to assume from that, there's that word will get you into trouble, that I can stop the recording.